All right, thanks everyone for coming. Yeah, we have some snacks over here. Feel free. So today we have a special arrangement. So thanks for coming early. Dieke is presenting, and so she's coming to us from Germany. She's been working in Southwest Montana on the Renova and 6 Mile Creek Formation, and so this is part of her PhD, which she'll be wrapping up shortly. So with that, I'll let you take it away, Dieke. Thanks.
Thank you. Yeah, thank you, Stuart, also for inviting me to give this seminar. I realize I'm a bit of an outsider in this seminar series, but we found some really interesting things, and I hope to give you kind of a new perspective on the tertiary in Montana during my talk today. So we started working here about 3 years ago, and I really like to thank all of you because you've been really open and kind, and I've been bugging you with emails, and you were always very helpful. So especially, for example, Susan, I saw she's online. Yeah, we had some really lengthy email discussions, and I was always very happy to open my laptop in the morning, have another email with maps and old reports about Montana. So yeah, actually, I also we met 2 years ago, which was really nice, and you gave me some wonderful maps, one of which I actually put up right behind me, and it's been there for the past 2 years, and it always reminded me of the nice field work we could do in Montana. So yeah, thanks, and let's get started. So for those of you who don't know me, I wanted to give a little bit of background about myself. Actually, I grew up in the Netherlands, and I sort of grew up in the Montana of the Netherlands, if you will. If I were to literally translate the name of the region, it would be something like back corner of the country. So it's basically just farmland and not much more. My dad's a farmer too. But once I turned 18, I was ready to venture out of that region, and I moved to Utrecht, where I studied my bachelor in earth sciences. Then after my bachelor, I decided I want to explore even further. So I took part in an exchange program and moved quite literally to the other side of the planet, to New Zealand. So after that, I came back to do a master's in earth structure and dynamics. And in 2022, I moved to Germany to do a PhD here. And yeah, as Stuart said, I'm currently wrapping it up. So it's very exciting. So during my talk today, I will give a little bit of motivation and geodynamic background on why we went to Montana in the first place. And I will also explain a little bit about the methods, which are mostly paleomagnetism, as I imagine most of you are not very familiar with it. I'll discuss my results from southwestern Montana and my interpretation of them. So first, some background. My PhD is actually on the topic of dynamic topography. Normally, we think of topography being built as caused by plate convergence when we have mountain building. But another way to build topography is by mantle plumes, which rise through the mantle, and they are hot and buoyant, and they will disturb the surface, deflect the surface, creating dynamic topography. So a plume, it consists of a tail and a head. So as this plume is rising through the mantle, it will create a dynamic topography on the surface. So as the plume rises, this topography will become more and more centered, and it will increase in amplitude. Then as the plume hits the base of the lithosphere, there will be flood basalts erupting. So in the case for North America, for the Yellowstone plumes, this would be the Columbia River basalt group. Then after those eruptions, only the plume tail is remaining, and as the plate is moving over the plume tail, we get a volcanic hotspot track being formed, in our case, the Snake River Plain. So I want to study this dynamic topography being created before the eruptions even take place, but how do we do that? How is this stored in the geologic record? This I will explain with some small cartoons over here. So we have a plume which is rising through the mantle, our simplified lithosphere, and some sediments on top. We have two columns, A and B, A being on the plume margin and B being far away. So as this plume is rising through, we get erosion in the plume center and margin. And this will create a hiatus in our column A. Then as the plume continues to rise, I told you this uplift is becoming more centered. So in this case, actually, there's no uplift anymore in our column A, but only in the plume center. And the sediments which are eroded over here, or the rocks that are eroded over here, they will be deposited in column A. Then after the plume has erupted, the topography is no longer dynamically supported, and we go back to kind of a stable state with deposition of this yellow layer. So then we end up with this column over here, and then hiatus in the middle. So basically the dynamic topography is recorded by a hiatus. But how do we get information on something that's missing? Well, one strategy to go about that is to study the sediments which were deposited below and above that hiatus. So in that way, we can use magnetostratigraphy to determine the duration of the hiatus, as well as use rock magnetism to study the changes in the sediment. I will explain more about these methods in the following. So first, some basics about paleomagnetism. So the Earth's magnetic field can be approximated by a dipole, which is aligned with the Earth's spin axis. And actually, currently, the magnetic North Pole is located on our South Pole. We refer to this as the normal field. We know this field has flipped during geologic time, where the magnetic North Pole actually was on our North Pole. And we refer to this as the reversed field. So this signal can be recorded in rocks, and it's the easiest to explain it using volcanic rocks. So when lava is erupting, it's hot, and the particles are free to move and can align with the Earth's dipole. When the rock then solidifies, the particles are locked in. And volcanic rocks are an excellent recorder of the magnetic field, but you're depending on a volcano erupting, which means you will only get a small snapshot of time. In sediments, it works a little bit differently, and the process is more complex. But we can imagine as particles are sinking through the water column, they're also mobile and they can align with the magnetic field. So we know that sediments are good recorders, and they allow you to get a fairly continuous record through times, which is really helpful for us. So when we then take our rock and measure the magnetic vector, you will get something like this B over here. So it has a direction and a length, and the length is the intensity of the magnetization, and the direction is defined by declination and inclination. So declination is the angle with the north, and inclination the angle with the horizontal. So on the equator, we will have an inclination which is 0, and on the pole, we'll have an inclination of 90. So if we're somewhere in North America, the field will be pointing north and down when we have the current situation. But when the field is reversed, the field will be pointing south and up. So we can use this variation in inclination to create something like a barcode. So we can create polarity intervals, which are these white and black pattern over here, to create a magnetostratigraphy. So on the seafloor, due to the constant outpour of basalts, we have a constant record of the magnetic field reversals. We can use this as a reference, which is referred to as the geomagnetic polarity timescale. So what we then can do is like scanning a product in the supermarket, quite literally is just take your magnetostratigraphy and compare it to the reference, the GPTS. So as you can see, this pattern is non-unique. So you can have several options to make the match. The likelihood of this becomes even higher if you have very few reversals. So for example, 3, or in this case, even only 2 reversals. I've seen this very often in the US, and that they have some polarity interval, but it has very few reversals. But in this case, you can basically match it to wherever you want. So another complication is that when you make this match, you're referring to the GPTS, but the GPTS is also constantly being updated. So for example, if you have this chron over here, it may have moved by 500,000 years or something. So when you run into these old studies, you really need to check what crons they matched it to, and what are the current age estimates of that cron. And not just simply take the absolute ages from the study. So the good thing is nowadays we have isotopic dating, and we can use this to have tie points to the magnetostratigraphy. So in this case, we really know this cron must be matched to this one, and it cannot be matched anywhere else. So these were just two small points I wanted to make about if you ever run into magnetostratigraphy, you have to be careful with that. Okay, then a little bit about how we work, how do we sample, and a little bit of background on that. So we usually sample sections. So we take 2 samples per sedimentary horizon. And an horizon, yeah, we just take as one sedimentary layer. So we drill those samples using a battery-powered drill, which is basically just a chainsaw, which we converted to a drill. And it needs to be water-cooled. So as you can see, we always have to bring up the water to the mountain, so we're dependent on having water with us. So here are some examples of our sampling sites. As you can see, it's not always easy to drill in a sediment, as they may fracture or completely disintegrate altogether. So we might need several attempts to actually extract a good sample. Then it's very important to orient our sample, because we want to know how it's located in the magnetic field. So this we do by drawing an arrow on it, and we have 2 important angles. First of all, it's the azimuth in the horizontal plane, which is the angle with the north, and the height, which is the angle with the vertical. So we then draw an arrow on it, and we also take sun compass readings to correct for the declination anomaly, which is currently about 10 degrees in Montana. So we correct all our compass measurements with this. So as you can see in this picture here, we always target the fine-grained material, as this is the best recorder of magnetization. Then we do some stratigraphic logging with Jacob staff measurements and GPS, and we take the samples back to Germany. So here we split up all the cores we take in several samples. So the cores are 1 inch in diameter, and we usually drill about 2 to 3 inches into the rock. And then in the lab, we cut it into pieces of 1 inch by 1 inch. And we again can see that arrow, which we use as a reference for the orientation. Then in Munich, we developed an automated system, which we can use to measure our sample. First, we measured the direction of the magnetization in the magnetometer. We display this on an orthographic projection called the Zijderveld diagram. So they are basically 2 plots on top of each other. First, we have a horizontal plot with north and south, and the samples the data is reflected by these filled symbols. And then we have a vertical component, which is up and down, and those are reflected by the open symbols. On the axis, there's intensity. So we can see our initial measurement over here and this one. But one measurement, it doesn't really tell us much, especially because we very often have an overprint of the current magnetic field, which we want to remove. So therefore, we apply an alternating field to stepwise demagnetize our rock. So after our sample has been measured, it gets moved to this alternating field coil over here. We apply a small field, which will randomize the magnetic directions of all particles sensitive to that field. The sample is then moved back around and into the magnetometer, where it gets measured again. And then we have our second point on our plot. We would do this for around 10 to 15 steps, and each time some of the intensity is lost. We then end up with this trajectory over here. And in this case, it's a very nice direction with a north component and down. And as I just told you, that's what we call a normal field. So besides that, we also do rock magnetic measurements. And we do many of them on very many samples, and we determined with this the magnetic mineral type, concentration, grain size, and other things. So these are the two main machines that I've used. So the vibrating sample magnetometer, you basically take some of your bulk sample and you ground it to a powder. You put it in a capsule and then you put it in this magnetometer in which it will vibrate and respond to the magnetic field being applied. So the other machine I used is the magnetic susceptibility meter, which is very easy. You can just put in your bulk sample, wait for 15 seconds, and you have your measurement. So it's very fast and simple. And nowadays you even have handheld susceptibility meters, which you can take with you in the field. But they can give you quite a bit of information, as you will see later on. So let's dive into our results. I'll show you how I use some of these techniques in southwestern Montana. So during my PhD, I'm focusing on the Yellowstone plume, and we went to these three areas. We also went to Wyoming and Washington, but today I'm focusing on my results of southwestern Montana. So we focused on this plume because it's relatively young, which means that it has not experienced much overprinting. And of course, thanks to you, it's a very well mapped area. So it was very easy for us to locate good sections to go to. And it's also generally easily accessible. So in southwestern Montana, you're all familiar with the stratigraphy in all the basins over here, where we have Renova Formation overlain by 6 Mile Creek Formation. They're separated by an unconformity. And during this entire talk, I refer to this as the early Miocene unconformity, or EMU. So first, I'd like to focus on this section over here, which is on the Idaho-Montana border on Bannock Pass, and it's called the Railroad Canyon section. So this is where we went first, and I'm showing its geologic map, satellite image, and an overview photo. Generally, the beds tip to the northeast over here, but it's very gentle, about 4 to 8 degrees. What I'd like you to note is the clear color difference between Renova being white and 6 Mile Creek being pink to tan in color. We use this color difference to identify the location of the unconformity. You can also see the exposure is rather patchy, so we really had to sample a lot of subsections to, in the end, come up with the following composite section. So the section is almost 700 meters in height, and the unconformity falls fairly in the middle. We measured rock magnetic parameters of all our samples, and this resulted in something very surprising. So around the unconformity, we observed a jump in several rock magnetic parameters. So in this figure, the dashed lines represent medians, and the gray shaded area, the 1 sigma uncertainty around it. So there are two parameters I'd like to highlight for you, which is magnetic susceptibility and saturation magnetization. They're both indicative of magnetic mineral concentration, and as magnetite is by far the most magnetic mineral, it's indicative for magnetite concentration. As I showed you, they're independently measured, but they both show the same, with a sharp increase around the EMU. Around the unconformity, there's a zone where you have kind of low and high values mixed, and we refer to this with the red band, which is exactly what I would expect for an erosional unconformity, where things are being stirred up and mixed. So then we have a third parameter, which is the saturation remnant magnetization, oversaturation magnetization. And this is a grain size indicator, a magnetic grain size indicator. So smaller values actually reflect greater grain size. We can see that there's not very many changes around the unconformity. So for now, I'd just like to keep you in mind that we have this increase in magnetite around the unconformity, as we'll explore this further later on. So we also measured the paleomagnetic directions. So here I'm showing two stereographic projections, one in situ and one in tilt-corrected coordinates. So because of the shallow bedding, like 4 degrees or something, it's not very different between tilt corrected and non-tilt corrected. So we found both normal and reversed polarities, which we can use to create our magnetostratigraphy. So here I show our results with stratigraphic height. And for our purpose now, we converted our directions to virtual geomagnetic pole, VGP latitude, which is basically the location of the paleomagnetic pole, which we would expect for that measured direction. So in case of a normal field, we would expect that the latitude would be 90, so over here, and we reflect this by a black band. And in case of a reversed field, we expect the latitude to be on the South Pole, so it's minus 90, and this is reflected by white bands. So in that way, we can construct our black and white pattern, our barcode, our magnetostratigraphy. So because we have an unconformity in the middle, we wanted to correlate the bottom and top separately. And as I explained to you before, we do have quite some reversals, but there's not really a unique match with the GPTS. But luckily, we had some of these uranium lead ages, which came from Harris et al. In 2017, where they dated some ash layers. So we can use these as tie points to the GPTS, and we can see the correlation that we made here with the gray dashed lines. So if I plot this slightly differently, over here now is our magnetostratigraphy on the y-axis, and on the x-axis we have the GPTS. And every black dot represents a reversal of the magnetic field. So basically one of these lines we matched up here. I also plotted the uranium lead ages and their uncertainty. And then we basically used a program like you use in the supermarket to match your product to the reference. So we asked the program to look for the 100 best matches between around 40 and 5 million years ago of our magnetostratigraphy to the reference. So 98 of those 100 matches are lined up over here. They're all overlapping, and they're nicely overlapping with our interpretation. So there are some very small variations, but overall we can be very confident in our interpretation. 2 of those are shown over here, but as we have the absolute ages, we can know for sure that this cannot be the right match. So this is our final interpretation, and we can be very confident in it. So with this interpretation, we can say that the EMU ended right around here, around 20.1 million years ago. Then we calculated sedimentation rates from our section. So here I have the same plot with our reversals, and now the gray dashed line indicates the sedimentation rate. So the Renova Formation had a sedimentation rate of about 6.2 centimeters per kilo year, and the 6 Mile Creek Formation one of 6.7. We then also calculated instantaneous sedimentation rate, which is shown in blue. So for this, we basically calculate the sedimentation rate for each polarity chron. So for example, we have this chron over here, which is about 20 meters high. And then we correlated it to something like 0.3 million years. So then if we calculate the sedimentation rate, we arrive at 6.7 centimeters per kilo year, which is then plotted here. So this then, for doing this for all the crons, it results in this step function over here. And as you can see, there's some variation, but overall, we're still very close to that 6 centimeters per kilo year. So we can say that sedimentation rate was actually very constant, which was surprising to us. The other thing is that we have a bit of a gap in age control between this absolute age over here and this reversal over here. So from this, we can say that the duration of the unconformity was somewhere between 0.1 and 1.5 million years. So let's go back to the bigger picture. Of course, we really like working in Montana, so we had to go back. And we went back the next year to sample many bore basins. They kind of have funny names, but I named them after the farmers that gave us access to the sections. So we know the unconformity was recognized throughout southwestern Montana. And in all these different basins, it looks a bit differently. We went to 6 basins, and in some basins, it's very easy to recognize, such as here in the Ruby Basin, we again have that color difference between the two formations. And for example, in the Flint Creek Basin, it's capped by this nice conglomerate. And at the Medicine Bluffs over here, we have that very thick resistant bed that forms the buffalo jump. And it's also very easy to recognize. But then, for example, in the Jefferson Basin, the exposure is not that clear, and we couldn't really identify the contact itself, but we may be still able to find it using our rock magnetic measurements. So first, I'd like to show you our bedding measurements, a total of 72, and they always have a dip direction towards northeast or southwest, and there's very little difference between the 6 Mile Creek Formation and Renova Formation. Also, the direction is very similar to the T-axis of focal mechanisms in the Basin and Range, showing northeast-southwest extension. So then we went to our paleomagnetic measurements, and we identified over 200 high-quality directions. I again show them in stereographic projection with in situ and after bedding correction. And we can see that without bedding corrections, the means are distinct from the present day field, which means that we likely sampled the paleo field. Then if we do our tilt correction, you can see that the clustering increases, which means we did our correction correctly and our bedding planes were the right ones. So lastly, I'd want you to note that the difference between Renova and 6 Mile is not that big. So from now on, it's not significant even, as the circle here is representing the uncertainty ellipse. So from now on, we always group them together. So when we group our directions into the different sites, we get this figure over here. And we can again see that the clustering is much higher in tilt-corrected coordinates, meaning that our bedding correction was good. So on the right, I'm showing you the magnetic declination with the arrow and the uncertainty around it. Usually uncertainty were quite small, for some sections a little bit larger, but overall, we can see that the directions are indistinguishable from each other, meaning that the basins were not rotated with respect to each other. So then going back to the unconformity, I compiled radiometric dates with the stars and fossil ages for all of my sections, and I created this correlation chart. It's roughly ordered west to east, and on the left here we can see our RCS section with, in red, our new age model. So then in all the other basins, I indicate with the red line the approximate span of time that we sampled. So please note that the duration of unconformity in all the basins is different. So either the timing and duration can be different. But overall, we sampled from about 13 million years ago to about 9 million years ago. Then to compare what happened before and after the unconformity, we take our 8 sections and line them up around the unconformity. So some sections have very few samples below the unconformity, but they always span the unconformity. So eventually, the highest density of points will be around the unconformity, but increasingly lower if we go up or down. So that's just a background for the figure I'm going to show you in the next slide. So here are all the sections on top of each other. Again, I'm showing magnetic susceptibility, saturation magnetization, and our grain size indicator. So what becomes very clear is that we see this sharp increase around the unconformity in all of the basins that we study. It always happens around the EMU that we get more magnetite concentration. This was very puzzling to us, and how such an abrupt change can happen in such a large area. So that's what led us to the following discussion. First, we wanted to consider climate because we know that magnetite can be altered and that it can change the magnetization. So therefore, we looked at the literature and we found this study by Retelak, and even though there's some variation in temperature precipitation, we can see that there's not really any difference between below and above the unconformity, at least not a constant difference. So even if we update the age model from their age model to our age model, we cannot really say the climate during Renova time was different from during Six Mile Creek time. And this was confirmed by several other studies. So for example, Chamberlain et al. In 2012, they studied oxygen isotope records of sediments in Montana. And Harris et al. In 2020, they studied isotope compositions of herbivore teeth in the RCS section. And Methner et al. In 2021, they studied clumped isotope records from pedogenic carbonates in Montana, including the RCS, and all found that there's not really notably any difference between the two times. Moreover, we have very stable paleomagnetic directions, and they do not indicate any alteration of the magnetite. And therefore, we don't think that climate can explain our observed changes. So we think these changes are related to a change in sediment source. As I illustrate over here, where during Renova time, we're inputting material from this magnetite pore source, and then during 6 Mile Creek time, we're inputting material from a magnetite-rich source. Another way to look at changes in sediment source is detrital zircon H spectra. So this would show a different H spectra for the different source regions, and thus being able to identify those. So this led us to compile the detrital zircon data from southwestern Montana, which I show over here. The colors represent different time intervals. So maybe we can relate the two with each other. So our first idea was that basement rocks are very rich in magnetite. So the exposure of basement rocks could explain why we would have more magnetite in the 6 Mile Creek Formation. However, the detrital zircon spectra show that both formations have a similar contribution of basement rocks, as illustrated by these brown and blue colors over here. The fact that basement rocks were already exposed during the Renova time was confirmed by the work of Bob Schwartz and Teresa Schwartz, which we also saw a couple of weeks ago. So the exposure of basement rocks cannot really explain what we see in our sections. And actually, the difference between the two formations lies in the young zircons. So here I've created a zoom in of the zircon spectra, only showing ages up to 150 million years. So then we can see that the Renova formation is characterized by Cretaceous and Miocene zircons, and that the 6 Mile Creek formation is dominated by Miocene zircons. So both fill up about half of all the zircons, as you can see over here and over here. So they're really dominated by these fractions. So perhaps this new Miocene source in the 6 Mile Creek Formation was magnetic. So another potential source of magnetic material comes from volcanic rocks. So here we plot all the volcanic rocks between 10 to 100 million years ago. And in teal, we show everything younger than 20. And in pink, everything between 21 and 100. So at this point, I'd like to make very clear that although we see a change in the magnetic and the detrital signals, it doesn't necessarily mean that they are linked. So if we look at rhyolitic volcanism, it's explosive and it produces a lot of ash. So this ash is rich in zircons, but not in magnetite due to its felsic composition. Basaltic volcanism, on the other hand, is rich in magnetite, but it doesn't contain a lot of zircons, and it's also not explosive. So therefore, we also distinguish on this figure basaltic, so circles, and andesitic and rhyolitic rocks displayed in diamonds. So having an increased input of both magnetite and zircons in the 6 Mile Creek Formation requires bimodal volcanism. The basaltic magnetite-rich source would be transported fluvially, and the rhyolitic material contributing zircons could be transported either fluvially or through air. So it is apparent that there's little volcanism in this Miocene time in southwestern Montana, but there is some, so let's zoom in on it for a little bit. So if we zoom in, we can see that there was some bimodal volcanism in Montana. We have these basalts over here and rhyolitic centers over here. So these rhyolites could have contributed zircons to our area, and the basaltic centers could have produced the magnetites, explaining what we see for these sections over here in our Ruby Basin. However, there are only very few basaltic rocks, and the only ones that do exist are these from potassium-argon dates. So these ages are not very reliable. Also, as the paleoflow was generally going towards the northeast, we can see that the RCS section is actually upstream of those lavas. So this cannot really explain why we see the magnetite in our section in the RCS, because how could the magnetite have come here if it lies in the upstream area? Therefore, we think it's likely not our source. And we started to look at sources further away. So because we're looking for a source providing magnetite to our entire area for an extended amount of time, we look for a large magnetic source. On the left, we show aeromagnetic image, and on the right, a simplified geologic map. So we calculated the magnetic contribution of all major geological units in an area with a radius of about 450 kilometers. We did this by multiplying the magnetic intensity of that area and divided by the total area. So this gave us the magnetic contribution of that unit. So for example, for the Cretaceous batholiths over here, they're very non-magnetic. So they show up around here in our plot. But the Columbia River flood basalt is very magnetic, and it's also large, so it shows up over here. So that means that this Columbia River flood basalt is very magnetic, and it's also relatively nearby. So this led us believe that this could be our source. Also, we know that the Columbia River was bimodal, with rhyolitic centers in orange over here, which were erupting simultaneously with the flood basalts. Therefore, we think the basalts contributed the magnetite to our area, while the rhyolitic volcanism produced zircons. And they were transported either fluvially or through air. So we realize it's quite bold to suggest a fluvial system connecting Oregon all the way to southwestern Montana. But a Miocene connection has been proposed before by Jim Sears, who found pebbles of the Milligan chert, which were very distinct, and he found them in the Ruby Basin. So we now suggest to slightly extend this Paleo-Missouri River to reach into the flood basalt. And this would have explained then the magnetite increase we see in our section. So this is our proposed drainage evolution. On the left, the drainage situation during Renova time, which comes from literature. So there's this paper by Chettel et al. From 2011, who saw an Idaho batholith source all the way in the Green River Basin in Wyoming. And then from View 2020, we took the Paleo-Missouri River, which is based on a lot of paleoflow measurements during Renova time. Then during 6 Mile Creek time, we propose a drainage situation, something like this, in which we have our Paleo-Missouri River, which we now, from Sears et al., which we now slightly extended. Also, there's the Salmon River, and Anderson showed in 1947 already that the tributaries of the Salmon River, which is currently flowing towards the west, they are barbed. So they actually have a weird shape compared to what you would expect from the direction of the river. So he proposed that the river could have been reversed at some point, flowing actually towards the east, which would match very well with what we see. Then we have the current situation on the right, where the drainage divide is very similar to what it was during the renova. So we're saying that during the 6 Mile Creek time, the divide, the North American drainage divide, must have shifted about 400 kilometers to the west. And this would explain then why we see this high input of magnetic material into our sections. But it's very hard to explain how it can go from one situation to another situation for some time and back to the similar situation by tectonic processes. So that's why we have to go back to our dynamic topography model. So here I show a very simplified sketch of the influence of dynamic topography on the drainage situation. So the Yellowstone plume created dynamic topography, and from our colleagues from geodynamics, we know that a mantle plume of this size can generate significant amounts of dynamic uplift, as I showed in my introduction already. So from analog and also from numerical modeling, we know that the diameter is the radius is about 500 kilometers, and it can create as much as a kilometer in uplift on the continents. So this could have shifted our drainage divide from renova time towards the west, now extending it to the Columbia River flood basalt. So after the basalts erupted, the uplift slowly dissipates. And in this way, the situation can go back to a situation which was very similar to what it was before, shifting the divide back to the east. So this is our current interpretation for what happened. So I realize it was a lot of information, so I'd like to shortly summarize it for you. First, we identified in the RCS section that the early Miocene unconformity ended around 20 million years ago. And we saw that both in the RCS, as well as in all the other basins in Montana, this was accompanied by an increase in magnetite concentration. It was actually increased by a factor of 4 or 5. So we combined this with detrital zircon spectra, which shift from a dominantly Cretaceous to Miocene source, also at the EMU. So both indicate a source change in Montana. We link this to the Columbia River flood basalt, which would require a westward shift of the drainage divide in the Miocene. And this we link to dynamic topography induced by the Yellowstone plume. So I'd like to take any questions you have, and thank you for your attention.
That was awesome. Can you hear me?
I can hear you, but it's a bit far away.
Can you translate for me?
Yeah, if I'll translate it because you can't hear the whole thing.
Okay.
Well, my first question, and I'll just start with one, is are you confident that the EMU is the same age everywhere that you measured it?
No, I don't think it is. It's like I showed let me go back. This figure. I think it varies mostly also in duration. And of course it's defined by the Hemming-Fordian being missing in most areas. So that's why usually it's ending around 17 MA. But in our RCS section, we found that it ends actually a little bit earlier already. But in general, I would say it ends somewhere between 17 and 20. Yeah.
And it migrated in time as the Columbia River basalt rose and fell.
Yeah, so I wasn't really able to identify a trend with like a spatial trend throughout the basins, also because in most basins, the time constraints are not really that tight. I mean, in most basins, we just know we have fossils of certain ages, but they can still vary by a couple of million years. And I think we would really need that resolution in time to really say if it migrated. Yeah.
Thank you.
You're welcome.
Yeah, I have a question, this is Stuart.
Mhm.
So what effect does recycling have on magnetite? So if I were to take sort of the same sediment sources and just recycle, would it concentrate magnetite or get rid of it?
It's a good question. Let me think about it. I think so I don't know, like what we see in the RCS section is that it kind of gets mixed both, right? So that we see Renova Formation had not so much magnetite and Sixma Creek had, so they both kind of got mixed. And what I think about recycling, I don't know.
Yeah, I'm not sure. I just the work of Bob Schwartz makes me wonder because I mean it's just a recurring theme when we map these things. There's been a lot of recycling.
Mhm.
And I'm not a mineralogist, so I don't know what the response of magnetite would be, but it might be something to look into and think about.
Okay, I see what you mean. I would still expect, though, that it would not be such a large increase.
Yeah,
Yeah, because you still need, then you would need like a lot of input material with magnetite in it to become concentrated like that.
yeah,
And
totally.
what happened to all the rest, right? So, yeah. Mhm.
Any other questions here?
I'm still trying to absorb it.
Yeah,
This is probably, you've given us a lot to think about.
yeah, this is great. I think
This
we're
is
soaking
really
it in.
good. Yeah.
That's great. Thank you.
So yeah, why is the Railroad Canyon section such an outlier? I mean, everything else just lines up so nicely. And so like what do we know about the drainage over there? I know you probably said this, it just hasn't sunken in for me yet, but why is it such an outlier?
Yeah, so it is kind of strange. Right now it's on the other side of the drainage divide. But if you look at the map, it's part of the Horse Prairie Basin. So we already know the drainage divide must have shifted at some point, that the RCS was also part of the Horse Prairie Basin. And if we go to the paleo flow, is it has also been suggested as one of the kind of gateways into southwestern Montana from Idaho. But there's not really any study of the detrital zircons of that section, or anything like that. So that would be really helpful for us actually to really see what happens there.
Okay, cool. Well, that's good to know. You should, if you have any specific parts of the section you're interested in, we're going to be doing some quick mapping out there this summer. So Colleen will be tramping around out there.
Oh, really? Wow.
So we plan to grab some DZ samples, so that'd be great if you have any specific areas or type parts of the section you'd like us to target. Let us know, and we can grab some and see what happens.
Awesome. Yeah, thank you.
Is there anybody in Zoom there?
Yeah, any questions on Zoom?
Want to hear what Bob has to say.
Yeah, I don't know if he's on there. Is Bob Schwartz on the call? Do you know?
Let's see.
I don't see him. I told him about it though.
Okay.
Yeah, he had the link, I sent it to him yesterday afternoon.
Yeah, I know he's quite concerned with our paleo flow
Yeah.
interpretation.
Yeah.
As he's always been saying, it's local sources, right? Yeah.
Yeah. I mean, your data is really compelling, and I think the argument for a bimodal source is pretty compelling. I just wonder if the Snake River Plain could be more of a sole contributor, and if the how much the Columbia River flood basalts really need to be involved, you know?
Hmm. Yeah, I mean, we can also imagine that maybe at the beginning it was, but then as it was slowly shifting back, that that the Snake River Plain became more of an important source. But to really have that initial magnetic signal already that early on, you would kind of have to include it. And I think also the work of Bob Schwartz and mine doesn't have to be exactly opposite, because we do still think that the drainage within Montana can have these local sources with basement rocks and everything. We just think that the through-going flow must have contained some component from Idaho.
Yeah. Okay. I'm also wondering with this figure, I like this figure, this is great. I'm wondering, like, incorporating what we know about elevation into this to try to see what's uplifting, what's, just being eroded and going down.
Mm-hmm.
I don't know if have you looked at isotope work, or I don't know other good ways of maybe elevations of the unconformity, or try to get a sense of what the elevations looked like between the Renova and 6 Mile compared to today.
Mm-hmm. Yeah, I can see what you mean. But I don't think was a very large difference in southwestern Montana itself. I think the main differences were further to the west.
Okay.
Guess I kind of have a question, or maybe it's more of an observation, just kind of staring at this figure. Hopefully you can hear me. I just think it's kind of interesting how the divide, I don't know, pre and post Yellowstone hotspot are kind of in the same place. Like, are there other controls there that are sort of like bringing that divide, I guess, back to right where it was pre Yellowstone hotspot?
I mean, we know there are some shifts. So, for example, the Divide Basin, there's the divide right now, but not in the paleo situation. But you're right; it's fairly similar. You must know, of course, we inferred this largely, so it might have been slightly different as well. But of course, we have the Rocky Mountains being a regional high, so it makes sense that there is a divide over there.
Yeah, I'll have to think about this. I don't know if this makes any sense, but I just know that in Wyoming, with the transition from like the foreland basins into the like intermontane basins we see today, I know that a lot of basins filled with thousands and thousands of feet of sediment through, all the way through the Oligocene. And then in the Miocene, they were just like completely evacuated. And there's some new like apatite fission track data sets and some helium data sets where they show that there was, deposition of 1 or 2 kilometers of material in lots of basins, and it was removed following the Miocene. So I kind of wonder with this if something similar could be happening, where you had filling of these basins and then up until the Miocene and then evacuation to sort of bring it back to the divide that it was before the basin filled. You know what I mean? But I don't know if filling big basins and then getting rid of the basin fill, I don't know if that's really consistent with the geology and with the I don't know if it works at the right scale, but I don't know.
Yeah, it's interesting you mentioned Wyoming, because we have a section kind of right here
Mhm.
in which we see also an increase in magnetite, but then it happens at the end of the Eocene. And then, as you said, the entire Oligocene is missing.
Yeah.
And after that, we have a completely different situation with a lot of aeolian transport and
Oh,
also high magnetite input. So
interesting.
yeah, it's a very interesting section as well, and we're still trying to make sense of that one, because it's quite different from what we see in our section over here, because there we have, like here we really have low concentration and high, and there we go from low to high kind of gradually.
Yeah.
You really see it increasing slowly.
Oh, that's interesting.
Yeah.
Do you know the papers I'm referring to about the basins filling up and evacuating in Wyoming?
Yeah.
That could be really interesting to think about that idea, how it compares with your Wyoming samples, and then contrast it with the other samples. That's interesting. Where did you guys sample over there?
In the Wind River Basin.
Okay, cool.
Mm-hmm.
Any other questions?
Well, I got one more thing. It's dare I say it, more of a comment. But this is, you know that Jim Sears has postulated that the same kind of scenario as you're describing occurred at around 800 million years with the when the Elkhorn Mountains volcanics were erupted. But 80 million years, 80 million years. Yeah. And so there's evidence in a formation called the Golden Spike Formation that the Proto-Columbian River was draining from east to west. And then the the Elkhorn Mountains volcanics dome rose up and changed the drainage to westward drainage in that basin, and then I guess it stayed that way since then. I'm not sure what I'm saying. It just occurred to me that there was a decent evidence for a change in paleo drainage around 80 million years. I can send you that if you're interested. I could send you that.
Yeah, I wasn't aware of that. Thank you. I do know they have some related to the hotspot, but of course, the topography created by a hotspot is much less than what we would expect from actual mantle plume rising up. So it's a much smaller effect. But it's interesting to see that this Elkhorn Mountain volcanics also saw some effect of it.
Yeah, it's just really crazy to think about the divide being all the way out in Oregon, because we're at 5,000 feet right now.
Yeah.
If you go right where that dotted line is today, you're at like 1,000 feet, 2,000 feet. It's crazy. So, I mean, once you get over into Idaho, Western Idaho, you just drop off the face of the world. The elevations just plummet. So it's totally wild to think about the implications of this and the elevations. It's really hard to visualize. It's crazy.
Yeah, this is what we would expect though from our plume model, is that where the flood basalts erupt, you get a subsidence afterwards. And actually, I've also plotted a cross section showing this topography, kind of to illustrate what you're saying, that you drop off. But before that, we can easily imagine the divide to shift anywhere between here and here, because the elevation differences are not that high.
Cool. Well, great stuff. Great figures. I'm really looking forward to this paper. It looks awesome.
Thank you very much.
Cool. All right. Any other questions? Yes. All right. Thank you very much.
Thank you.
You're welcome.
Great. Thanks everyone for coming. We'll see you on the next one.
My brain for a while.
Yeah, we're gonna just hold this over for a week or so.
Yeah, send me an email anytime if you have questions.
Excellent.